we'll now begin our panel on developmental OT, IoT technologies. Let me introduce our panel moderator, Brad Surik, and then invite our panel up onto the stage. Brad is the Chief Product and Strategy Officer at Hitachi Vantara. He's a distinguished science alumni from Purdue University, where he received his BS in computer science. He's demonstrated success driving global digital transformation that deliver top-line growth and productivity. He led the formation of GE Digital, serving as their Chief Operating Officer. He's an entrepreneur with a proven record in building successful businesses with large multinational companies such as SAP and Business Objects. He has over 25 years of success in digital transformation, general management, product and solution development, software engineering, and operations across multiple industries and geographies. Please welcome Brad Surik and our panel on IT.
Thank you, Bev. Appreciate that. Thank you, Bev. You guys can please come up. I'll introduce you here while you're up on stage. So thank you. It's an honor to be invited to facilitate this panel. It's actually a relief to be the facilitator of the panel because, one, I introduced the panelists. They're so accomplished. It's be a little stressful if I was going to be asked to present right next to these folks. So at least I just have to ask the questions and facilitate the conversation. You know, Bill spent time in his keynote, a lot of time telling us all that it's all about the business problem and the use cases, not at all about the technology. So we're going to spend the next hour talking about the technology. It's actually really a focus on the cutting edge of some of the technologies that go into digital twins and the OT and IT technology. And we have a really experienced group of panelists here today to have this conversation with you. So I'd like to introduce them now. First, I'll introduce Scott Hamilton. So Scott started his career as a Windows administrator, and he must have, gotten frustrated with the blue screen of death that he got from Windows because he moved into quantum computing around 1995. Scott was one of the early developers in the Beowulf cluster in '98, and was on the team that first developed a GPU cluster in the U.S. in 2001. So Scott has a lot of deep expertise in quantum computing, and he's going to give us a presentation this morning on the state of quantum computing and how it's used. And that applies in the twin context, as I've learned from Hemant, that the processing for digital twins, they're looking at the application of quantum computing. So we're going to start with the quantum computing topic, and then we'll move on to Hemant Kalera. So Hemant comes to us, he's at ANSYS, he's a product manager at ANSYS, and he working on the adoption of digital twin technologies with their customers. So we're going to get a couple of different perspectives on digital twin technology this morning. So Hemant is going to give us one perspective on the digital twin technology, and then Terry Shao is going to come up and give us a perspective as well. So Terry comes to us from MathWorks, and where she spent 10 years, and she's working. She spent time out with customers as a really a sales engineer, looking at how to apply the technology in practice with customers and guiding customers. And now she's really focused on the industry side. So looking at how the application of digital twin really progresses through different industries. She's got a deep expertise in industrial control systems. So I think we're going to get a great survey of the technology landscape from our three panelists, and I'm really excited to hear what they have to say for us. Myself, I come from Hitachi Vantara. I joined Hitachi about a year ago, and the context for us, digital twins are really critical for the digital industrial transformation that's currently happening at Hitachi. You may or may not be familiar with all of the things that Hitachi does, but we've been in industrial business for 107 years, everything from power generation equipment to construction equipment to bullet trains and you name it. We've been in IT technology for 30-plus years, starting with domestic mainframe and server technology in Japan, and then moving into global leadership in storage and enterprise storage, and now in IoT and advanced analytics technology. So we're undergoing this digital industrial transformation ourselves with the large industrial businesses that we have. Hitachi Vantara is put together and assembled about a year ago from many different capabilities inside the company to innovate around the technology necessary to drive that digital industrial or transformation inside of Vantara, but also to work and co-create that technology with our customers. And I'd like to thank Michael Chance at Disney, one of our strategic partners, for connecting me with the Simulation Summit, Bill as well. This has been a really great opportunity to get to know a bit more about the deep expertise here in Central Florida. And I can say, Mayor, this summit is having its desired effect. It really raised our awareness to the level of talent in the area. We've got, personally, I have about 140 software engineers based in the Orlando area focused on advanced analytics. And, I'm using this opportunity to help us look at deepening our investment in the area and make deeper connections. So thank you very much for this opportunity. So with that, let me get on to the main attraction here and invite Scott up to give us a presentation around quantum computing. So thank you. Scott.
Well, first, as he's already said, I've been in the industry a lot of years. I actually started in computing at 8 years old, programming in Fortran 4 on punched cards on a university mainframe. So I've been at the bleeding edge of technology, believe it or not. The punched cards on the mainframe, that was bleeding edge technology in the 70s. Now we're doing quantum computing, which is the bleeding edge technologies of the 2000s. So basically, I'll give you a quick introduction to Atos as a company. I'm not sure how many people know Atos. It's a global company, but it's been primarily European-based. So a lot of people in the U.S. know very little about us. So we are a $13 billion global company with about just over 100,000 employees. And we have $2.3 billion in North America with just over 11,000 employees. So we're the top 5 and top 7 worldwide IT service providing companies. But we do a lot more than that because we're also in not only the business development, but also the research and development. And the part of the company that I work for is our big data analytics. And we handle end-to-end offerings of high-performance computing, data analytics, all the way down to the data center, all the way up to the software stack. So we're a well-rounded company that's pretty much have our hands in a little bit of everything. And my primary focus, of course, is on the supercomputing and high-performance computing divisions. About a year ago, Atos decided to step into the quantum computing industry and start developing quantum computers. As part of that, we formed a committee with several engineers from Europe on quantum computing, and we made a decision that we weren't going to get into developing quantum processors, but rather into developing the tool sets in order for software engineers and data analysts to begin using quantum computing today before those processors are readily available. So how does that fit today into this conference? Well, you see that what started to happen actually as early as 2001, Moore's Law stopped improving the performance of your computing systems and computing platforms. What happened in 2001 was we started getting multi-core technologies because we could no longer speed up the single-core processor. The fastest single core was actually developed in 2001 at 4.5 gigahertz. We've never been able to get a processor core any faster than that without severe overclocking and a lot of cooling technologies. And so Moore's Law stopped benefiting most of us in 2001, and we had to start revamping our software stacks and start to look at parallel systems in order to use these multi-core processors to the best of their abilities. And now we're reaching the point where we've got so many transistors setting on the processors that we're hitting the limit of being able to go any farther with digital technology. That is where we need something new. That's where quantum computing starts to come in. Here's some of the domain areas that we think quantum computing is going to impact the most. One of those is cryptography. Some of you may know, some of you may not know, cryptography is actually based on prime number and prime number factorization. And our current technology, if we get a quantum processor somewhere around 1,000 qubits, all of our security technologies that are based on cryptography are going to be broken. Because these quantum processors are excellent at factoring prime numbers, and they're going to be able to break your cryptography systems. So it's very important, if you're in security realm or cryptography realm, to start working with quantum computing today to get ahead of the curve and start developing these cryptography algorithms that are quantum proof. Second area is the chemistry of science and materials. If you're simulating the quantum physics at the atomic level, what better way of simulating it than using a quantum system to simulate a quantum system? The third is the third's database searches, and the fourth is statistical analysis. A lot of that's happening today with systems developed by D-Wave quantum annealing. It's kind of a different beast in quantum processing, because how the annealers work is you set a predetermined state and you wait for these qubits to settle at their lowest energy level. And that lowest energy level gives you a predictive analysis of where your best path, where your data that you were looking for is found. It's used for path analysis, traffic analysis, routing of traffic, and things of that nature. Now, you can see here's the research areas where we have actually where you're studying the qubits and how to make them and how they function. We also have about 22% of the field that's focused on the algorithms. Today, there are actually very few algorithms out there for quantum computing. That's one of the things Atos as a company is looking to overcome and help people develop algorithms. And I know most of you in this room probably don't have access to a quantum processor. I could probably ask for a show of hands, and we might have 10 that say, hey, yeah, I can access a quantum processor. Atos is a company, we have access to 2 quantum processors. Says, how are you doing this quantum algorithm design and quantum software stack? We're using digital twins. We've developed a product. I'm going to skip through a bunch of slides here because I don't have a lot of time, and I want to make sure that I get down to the core of this conference. Basically, we're anticipating to help leap the technology ahead through the development of our quantum learning machine. We named it a learning machine not because it does machine learning, but because it's a tool for learning quantum algorithms and learning quantum development. So really, I would say more it's a teaching tool than a learning platform. We get that question a lot when people say, hey, it's a quantum learning machine. How can I use it for machine learning? Well, that's not really what it was designed for. So what we've done is we're using digital twins of quantum processors. Now I'm going to digress from the slide deck, and I'm going to ask for some audience participation so that you can understand the complexities of a quantum computer, why we have very few quantum processors today, and those nuances of those processors that cause us, one, it gives them the power, but two, it also gives the complexity that makes them very difficult to create. So I'm going to talk real briefly about a qubit, what it is and what it does and how it differs from a binary bit. So you're all setting down, most of you are setting down in the room right now. We'll say that's your 0 state in binary. Now, if I ask you all to stand up, everybody stand up. Now you're all in your 1 state. We're a binary system. Did you notice everybody stood up at a different rate? That different rate that you stood up, that's the quantum state of a qubit. A qubit can be in the 1 state, where you're standing, the 0 state where you're sitting, but the real power behind quantum computing is it can be at both states at the same time. Now I challenge you, get into your quantum state, and halfway, set down halfway. How long can you stand there? Not very long. Well, we have the same problem with quantum computing. You can go ahead and set down now. That is one of the areas of noise problems. You try to set down halfway and you've got noise from the environment causing you to settle to your 0 state. The main factor of that noise is gravity. Believe it or not, that's actually one of the main things that impacts a qubit in a quantum system, in a quantum computing system. So how do we overcome that difficulty? Today, we do it by freezing those qubits and making them so cold that it's difficult for them to move and change state. But we're still only able to hold one there at near absolute 0, and we're also only able to do that in a very clean and pure environment. So that's the reason why we don't have a lot of quantum processors today. And one of the things that we're doing with our quantum simulator that most companies are not, and there's a lot of simulation software out there for simulating quantum systems and learning quantum algorithms, but most of them are doing that pure quantum state where that qubit that they're simulating can stay in that superimposed state or that state between 1 and 0 forever. Obviously, that's never going to happen in the real world. You're not going to stand halfway between standing and sitting for an eternity. The other piece of quantum computing that's very important and critical is called entanglement. And that's where 2 qubits are joined together and they're always in the same state. So you can think of the person sitting in front of you. If they stand up, you have to stand up. If they sit down, you have to sit down. If they're halfway in between, you're halfway in between with them. Noise from the environment, that qubit can entangle with the environment as well. And that causes what we call phase distortion in quantum computing, where the phase of the qubit doesn't stay where it's supposed to stay. And so you can't predict what the real outcome is supposed to be. And ultimately, we settle these qubits into a 0 state or a 1 state, and as soon as we measure it, they're settled there. They don't move again. So you get one chance, and so these quantum processors have to run the algorithm multiple times, usually around a minimum of about 1,000 times to do the analysis correctly to get your true result. And you can think a quantum processor is a probabilistic processor, and your digital one is deterministic. You know what your result's going to be in your classical computer. You only have a probability of what the result may be in a quantum processor. And so there's a whole lot of power in machine learning and in digital twins and in the Internet of Things for using quantum processors. And that's the power of our quantum processor. Today, I'll just give you one example of one of our customers. It's Oak Ridge National Labs. They are the center of excellence for quantum computing within our Department of Energy. And they have one of our quantum learning machines. And what they're using it for there is algorithm development, design, and simulation of the quantum processors that they have access to. They have access to over 15 different quantum processor technologies at Oak Ridge National Lab. And what they're able to do with our quantum simulator is create digital twins of every single one of those 15 processors, take their algorithm, run it on our simulator, and determine which quantum processor technology works best for their particular algorithm. And that is all because we've integrated into the system the ability to simulate the noise that impacts the quantum states into the system. So we're creating a digital twin of that actual physical qubit. And because we're not developing a processor ourselves, we're doing it in a completely hardware agnostic way. And you can collect the parameters of the quantum processor that you want to simulate, put it into our simulator, and get very close to real-world results that you would see on the real quantum processor. And so it is a tool set that allows us to do real quantum computing today. Some of our other customers are actually developers of quantum processors that are using our system to model their processor to figure out how to improve it. And so that's what I'm here today to talk about, is the quantum computing, quantum processors, and where our technology lies. And I went totally off slide deck. So I think I'm wrapping it up there.
Yeah, that's great. That's great,
thanks.
Scott. We'll use the Twitter handle, and we'll come at the end for questions. I think the main takeaway I had is I can get really good abs if I get into quantum
Yes.
computing. Okay.
And most people use the example of a coin flipping in the air as the qubit. And when it lands, it's either heads or tails. But that doesn't give you the impact of what the problem is in the environment. When I make you stand halfway, you realize the environment has a lot of impact on that quantum system.
One quick question. Is there a class of algorithms that are have more synergy with the quantum computing thing, or what are the kinds of algorithms that you think are going to emerge first, or how do you think about that?
The main two algorithms that they're using today on quantum computing are simulations of quantum systems for atomic level and atomic research, and the second is path determination and shortest path and path-based algorithms. The traveling salesman problem, for example, is a very good use case for quantum computing.
That's great. Thank you, Scott.
All right.
So please, questions, send them to Twitter. And we'll come back at the end. And I think at this point, I'd like to transition to you, Hamath, and have you talk a bit about the digital twin. You also mentioned to me ahead that you guys were looking towards quantum computing as a potential accelerator of what you're doing.
So what I'm going to do is maybe bring a slightly different perspective to the topic of digital twins. So we, in the morning in the keynotes, we spoke about how we could assimilate measured information from various sensorized sources, bring that information together and create a digital twin of sorts, right? Now, what if instead of using actual measured information, if you could create a virtual model, a virtual replica of a certain asset, and use that to gather information, right? So can you build a digital twin, or maybe could you complement or supplement an existing digital twin in that manner, right? So I'm going to talk about enabling a simulation-based or a virtual model-based digital twin. Right. So before I start off with the topic, I just want to quickly introduce our company. So I'm part of ANSYS, and ANSYS is a leader in the area of engineering simulation. So if you're in the business of creating an engineered product, it's very likely that someone within your company is using one of our tools, or someone in your supply chain, either upstream or downstream of you, is using our products, right? So we create methodologies, we create software that allows you to create virtual replicas of various products. This could be a motor, this could be a pump. So before you released your software, before you started producing it, mass producing it, if you wanted to kind of test out how the product would work in a more virtual environment, we provide you with the ways and means to do that, right? And this is all we do. We are a very focused company. We've been in the business of creating processes, tools for engineering simulation for a long time now. As I mentioned, we are a leader in the area. We're a billion-dollar company with a strong international presence. And as I mentioned, most of our focus in the past has been on creating software that would help people design things in a better manner, right? And we are trying to transform a company instead of just focusing on the design aspects of a product. We are also trying to see how our products would play in operational scenarios, right? So after you designed a product, after you've released a product, can you use simulation models to predict failure, right? To prescribe maintenance intervals, service intervals, right? So we're going from being a purely design-oriented company to a company that has a part to play in the operational aspects of product operation as well. Right, so the question is, how does simulation matter in an IoT paradigm, right? So the best way to maybe talk about this is to highlight various use cases. So, there are quite a few, but, a few main ones here. So you could use it for things like real-time asset monitoring. You could use it for predictive maintenance, right? And things like prescribing service intervals. You could use it for connected field service, so these are some key areas. Now let's look at each of these areas in more depth and detail. Right, so real-time asset monitoring. So traditionally, the way real-time asset monitoring is done is you have an asset, you sensorize the asset, you put in sensors, mount sensors in the asset, you stream in data, you look at the data, and you can figure out if the product is doing what it's supposed to do, right? Now, this is I think is a great way to do things, but sensors are expensive. You can't sensorize everything, right? So let's say the inside of a combustion engine, it just gets too hot. So there's no way for you to tell, how efficiently maybe an engine is burning while it is in operation. So you really can't sensorize and get information on that particular aspect, right? So the question is, can you, instead of using purely sensorized sources of data, can you use virtual sources of data, right? Virtual sensors that are coming from virtual models, right, to gather information. The second use case is predictive monitoring service. So there's been this trend towards using machine learning for predictive maintenance, for prescriptive maintenance, usages. So let's say you have a product, you ship the product out, right? And typically you want to ship it out with some data, with some historical data, with some algorithms that would help your user to predict how the product would perform once it's installed in the field, right? So this requires you to have some historical basis. This requires you to have some historical data that you can then package into algorithms and allow your users or your consumers to look at product operation. But what if it was a new product for which you didn't have any historical data available, right? So in this scenario, what you could do is instead of relying purely on sensorized information, you could rely on virtual models, right, to create various usage scenarios, right? Package them up into machine learning algorithms and ship that with your product, right? And then your consumers, while running the product, could run these algorithms as well and get some insight on product usage specifics, right? On if the product is operating as it was designed to, on maybe prescribing maintenance intervals, so on and so forth. Right, and another use case is connected field service, right? So let's say you have a problem in the field, right? And you have some prescriptive models that you have in place that prescribe certain solutions, right? So you have a problem, and these models are telling you that this is what you need to do to correct the problem, right? An actual live asset, right? And stream in the actual operational metrics coming in from that asset into the model. And in design phases, you could run actual scenarios on how your product is being currently utilized and build the next generation of your product, right? So now let's quickly talk about what a simulation-based digital twin is. I'm going to read through the text here. So it's a connected virtual replica of an in-service physical asset in the form of an integrated multi-domain system simulation. Now there's a lot here, so maybe let's pass through the details. So first of all, it's connected. What that means is we have a model and we have an actual physical entity that is connected, right? So you have data coming out of the model that is streaming into the actual physical asset, and data from the physical asset streaming back into the model, right? It's a virtual replica of an in-service physical asset, right? So we are assuming that simulation-based digital twin would be deployed in operational scenarios where there is product operation currently taking place. It's an integrated multi-domain system simulation. Now this is probably getting a little too technical, but what this means is we are simulating all aspects of the product, right? So any kind of physics, maybe things heating up, right? Any electrical behavior, any mechanical structural behavior is simulated in the digital twin, right? And if the actual product is actively controlled, right? So if there's a controls algorithm in place that is dictating how the product is performing, we simulate that as well, right? So it's a very honest-to-God replication of the actual physical asset. And by doing this, what we're hoping to do is we are hoping to optimize how the product operates in the field. We are hoping to unlock new revenue streams for our consumers in areas such as predictive maintenance. And at a broad level, we're truly trying to optimize industrial asset management. I'll just skip through the slide. At a high level, what the slide says is that we have a lot of foundational capability that allows us to create digital twins, right? So when you create digital twins, you need to, as I mentioned, you need to simulate all aspects of physics, right? So if there's electrical behavior, thermal behavior, mechanical, structural behavior in your product, those aspects need to be simulated, right? And we have tools, we have methodologies, we have processes in place to capture all that physics, right? And create a complete virtual prototype and a digital twin. Now the product that allows us to do this, the product that I work with is called ANSYS Twin Builder, right? So at a high level, what this allows you to do is it allows you to create a model, a physics-based model of a digital twin. So it's not a purely database model. What you're doing is you're solving underlying fundamental equations that describe various kinds of physics, right? So it's a physics-based model. So you have the ability to build models within this particular tool. You have there's functionality and features within the tool that allow you to take the model predictions and compare it against what the asset is actually doing, right? So it allows you to compare the virtual model to its actual physical replica, right? And see if the model predictions are in line with what the physical asset is actually showing, right? And it also allows you to connect to the physical asset. So you have this ability to take a virtual model, so this could be like a virtual model of a motor, and connect it to an actual motor, and stream data back and forth between the virtual model and the actual physical asset. So, at a high level, what is it that we're trying to do as ANSYS, right? And by creating the simulation-based approach. So analytics is very powerful. It obviously allows you to answer very fundamental questions, especially in the area of operational technology, on things like what is happening, right, within your product. When is it happening? We are hoping to use more physics-based virtual approaches to maybe extend the discussion a little bit, extend the insight a little bit, and answer more fundamental questions about why and how, right? So if something is getting damaged, why is it getting damaged, right? What the remaining useful life is going to be in a current state of operation. Right? When should you plan shutdowns? When should you plan maintenance intervals? So all this insight, you have the potential to gather it from physics-based simulations and utilize it, right? And what we are proposing here is not a pure model-based approach. What we're saying is by taking a virtual model and combining it with actual physical data that you're gathering, by using these two data sources, you could potentially unlock efficiencies in your product operation, in your process optimizations, create new markets, for example, new service revenue streams, and drive profitable growth within your company, right? The next slide is a video that kind of brings the whole thing together. We recently announced a partnership with SAP, right? So we're going to be part of the SAP platform. So our tools and methods are going to be part of the SAP platform, and they're going to be utilized by SAP consumers for various operational decision making.
ANSYS and SAP teamed up to create a vision for the intelligent enterprise to drive value creation by providing a seamless digital thread between engineering and industrial asset management. Using SAP Predictive Engineering Insights as the first solution based on this partnership, industrial asset operators can optimize operations and maintenance through real-time engineering insights. These insights are based on multi-physics simulation models from ANSYS. By integrating these simulation models into SAP Predictive Engineering Insights as runtime models for physics-based decision-making, companies can unlock value across the product lifecycle and provide financial context from SAP solutions to engineering-based decisions in asset strategy and performance management. Consider this pump. By tracking how the pump is engineered, built, and operated, asset managers can increase performance and availability of these assets by analyzing engineering insights from SAP's market-leading Intelligent Enterprise Solutions portfolio. SAP is designing its network of digital twins to synchronize in real time the virtual, physical, conditional, and commercial definitions of assets and products, intended to help customers accelerate innovation, optimize operating performance conditions, predict service requirements, improve diagnostics, and enhance decision-making throughout the value network. ANSYS solutions for digital twins can predict emerging failures, show why specific components may soon fail, and highlight financial implications based on the integration of SAP business software. Asset managers can identify operational deviations in real time and communicate issues through alerts. Operators can use these engineering insights to investigate whether a situation is critical and which actions they should take to minimize business disruption. Virtual sensors can be used to gain further insights about the behavior of such assets without adding new sensors to the equipment. By using these physics-based engineering models from ANSYS, operators can continuously monitor and assess the dynamic behavior of industrial assets and identify conditions such as erosion and many other physical phenomena. The combination of these engineering insights gathered using SAP solutions can enable operators to optimize asset performance. The SAP Predictive Engineering Insight solution also includes advanced tools for simulating future behavior of systems based on these measurements. Depending on the severity, asset managers can collaboratively decide on further actions to optimize operations or take proper maintenance actions to improve capital and operational expenditures. Through integration, historical data and alerts automatically appear in the SAP Asset Intelligence Network, where business partners can collect, track, and trace equipment information. Future product development can also benefit from these insights, gathered from operation of the assets, resulting in optimized equipment performance and increased profitability.
Yeah, that's sorry.
Yep.
I was just looking at this is really impressive stuff. You're focused on, as you were saying, not only the technology but the adoption of it with customers and helping customers look at this. You know, I would imagine that getting access to the physics-based models is probably one of the barriers. If you're a manufacturer, you've got those, but if you're an operator, you don't always have access to that. How do you think about that?
Yeah, that's a good question. You know, so the most fundamental need here is being able to create these models that would allow you to generate this virtual information, right? And as you kind of progress down the supply chain, you know, that modeling information kind of gets lost. So what we are trying to do is we are trying to come up with standards that and actually there are existing standards that allow you to take models that are created by one supplier, maybe abstract out all the underlying, IP, and just format it in a manner that you could then exchange it with someone else and let them use it, right? So there are these standards in place that allow you to exchange information, right? Without really compromising on your intellectual property when it comes to simulation models. That's an evolving standard. That's an up-and-coming standard. Not a lot of people kind of use it, but that's one way of making simulation models available to everyone in your supply chain.
Great. Yeah. Well, thank you very much.
Thank you.
So now I'd like to introduce Terry, or invite Terry up to talk another perspective of digital twins. And Terry has a deep expertise in industrial control systems, so it'd be interesting to see the perspective.
NASA used digital twin to deploy this space shuttle in satellite into the space. Back then they can monitor what's happening with the satellite. So it is a digital twin. It's already happened a long time ago. But what I'm talking today is how and why is related to you, to a smart city, to your cars, to your manufacturing machines. So let's start with just a few examples. So digital twin has transformed the way that manufacturing machines do the predictive maintenance. Digital twin has transformed cities. How do they reduce energy consumption? And digital twin has helped for risk mitigation for, in this case, the New Zealand grid system to make sure that in any given time, energy reserve is enough to supply to the city. So before so I'll walk you through all these examples, why digital twin is real, because it's already happening. So before we go in there, right, what's the industry's trend? Why everybody's talking about it? So there's more and more connected device, right? There's more and more commoditization of cloud technology. And there is just more and more amount of data you need to extract the insight from. And finally, all the industry is talking about digital transformation. So that leads to the rise of digital twin. And in fact, in the Gartner survey, 66% of the organization they surveyed said they will use digital twin in the next 3 years. So it is happening. So what is digital twin? I think a number of speakers have given you the definition what digital twin is today. But I'm going to walk you through what is the digital twin with an example. So one of the examples I give here is the smart city example with BuildingIQ, who work on adaptive building energy management. So their objective is to reduce energy consumption with the HVAC system. So they have, building with HVAC systems, and they connect their server on the cloud. And the idea is that how do they manage tenant comfort, taking into account the energy price change throughout the day, and the weather forecast. How do they use all this information to achieve the optimization that they finally achieve? But before I get to the solution, let's take a look at a different lens. If we would look at it on an IoT framework, I think this is kind of close to the picture that Bill showed you earlier. The assets, in this case, is the HVAC system inside the building. The edge, which the supervisory logic control sits on, is locally connected to the HVAC system. And then with the long-range communication is the cloud that's responsible for the operational technology, and the IT system kind of supports everything. So how does BuildingIQ story link into this framework? Well, like I said, the HVAC system has the high real-time closed-loop controller, right, sits on top on the building itself. Now, based on the past historical data and the current building condition, the supervisory logic is operating on a digital twin, which is built based on the past historical data. With filtering, processing, and visualization, we were able to tune the set point for the building. Well, that's based on historical data. What about all this, energy, price we're talking about, the weather forecast and the tenant comfort, all that's come into place? Well, it come into place from the left or your right. I don't know. So all those constraints comes in, and another digital twin with machine learning created algorithm, it sits on top now on the cloud. So this is the multi-objective optimization that optimize based on all this constraint to come up with the energy efficiency optimization and go through the robustness analysis and retune the set point for the HVAC system. So what's the final result? Is a 25% cost reduction. So this is already happening, right? It's not something what we could do, what we want to do, it's already happened. So I just say there's two digital twin, right? Well, it could be digital twin. What we meant by it is a faithful, up-to-date representation of the asset itself. What is the asset? Well, I'll just give you the HVAC system. Your car could be an asset, your wind turbine, you, right? And it also, there's multiple ways of coming up with digital twin. Let it be physics-based or data-based. And any given project, our customer don't only have one digital twin, but is a multiple composite of digital twin that complies of multiple level of fidelity. So, like I said, if you look at the left-hand side, right, that is the first principle modeling, how the digital twin model would look like, based on this Simulink, if you haven't seen it. The right-hand side is the data-driven modeling, which use system identification, machine learning, or deep learning. So we have a spectrum of tools that help you come up with your digital twin. And so how does the MathWorks support digital twin? I should introduce us. We are a $1 billion company of 4,500 people across the globe. So our bread and butter is data analytic, modeling, simulation, and code generation technology. So together, with integration with the enterprise IT system, we can help you not only build your digital twin, but also deploy it to any part of the framework of your IoT framework, which is the assets, the edge, or the cloud. So, well, this is all good, but what does it give you? What does the value of digital twin bring? Well, I think Bill hit on this point, which is the value is to make the timely decision where they have most value for your company. I don't know what is the application that makes value for you, but I know that if you want to make quick decision that is close to the edge, let it be shutting down a wind turbine in a minute or in a second due to sudden change of weather, or you need to access to a streamline of data coming in with big data processing on historical data, maybe a fleet of wind turbine, you need to analyze the past performance. We have tools through code generation, through app deployment, and enterprise integration tool to connect to Spark and Hadoop to help you to achieve that decision making, right? So fast on the assets or large scope of data you need to analyze, we have tools across the board. The goal is to bring that value to you, allow you to make that decision quickly or slowly, but with the amount of information you need to know. So I promised you to give you some, real user experience. So Mondi, it is a 7 billion euro company with 25,000 employees across the globe. And what they do is they want to use our tool to do predictive maintenance on their paper-making machine so that they minimize the downtime and to help the operator make decisions. So how do they do that? Well, the data that they're using is the sensor data. They have anywhere 10 to 100 sensors on each machine, and they take the data every minute, and they will assess the quality of the state every 40 minutes. Now, let's figure out which one is the best to capture the dynamic of their system, and then to use that model to predict when the machine will fail and to take action before that. Now, this is all, desktop, and how does it help the machine operator, right? They take a step further, and they use MATLAB App to encapsulate the algorithm and create an app so the operator who might or may not know MATLAB and Simulink to able to utilize the algorithm on the manufacturing floor. This is how the app looked like. It's actually they're using today. So on the left-hand side is the machine. And then the app tells them the specific data about that machine, so they can, in front of the machine, tap on the machine number and say, what is the state of the machine today? Does it need to be maintained today or tomorrow or in 2 weeks? So by using our software, not just taking data into the environment, analyzing it, creating a predictive algorithm, the digital twin, and also enabling the machine operator to take actions on the floor. And the goal is, of course, minimize downtime. I'm going to conclude the talk with another story. I keep saying story. This is true story. This has already happened. So this is actually TransPower. It's a smart grid management system, and they want to ensure the reliability of the reserve management tool. They want to know that at any given time, if generator fail or a glitch in the system, the energy reserve is enough for the entire New Zealand island. So how do they do that? So first of all, they build a Simulink model of the electrical grid using a SimPower system. And then they take the measure data from the grid. Well, there's the grid. Here's the model. How do they make it consistent among each other? They use parameter estimation by taking the real data from the grid and superimpose it with the Simulink data so that the model really represents what's happening in the grid. Okay? So now they have a digital twin because the model itself represents what's happening in the grid. So now what? They run 1,000 scenarios. What is a scenario? Well, it could be a fault on the grid. It could be 10 generators fail at the same time, demand increase. It is the ability to run the what-if scenario that allow them to ask the question, is the energy reserve sufficient under any of these conditions? And if the answer is yes, nothing would happen and the reserve is good, they will repeat the test every 30 minutes. But if the answer is no, the energy reserve is not enough, and they can take action, right, to increase energy reserve such that they would not run into that corner case. Okay? So just to conclude the talk, I want you to walk away with digital twin is real. It's already happening and being used in practical applications. And 2, this is not the one digital twin application, right? What is your business case? What are you trying to do with digital twin? And to know your business case before implementing digital twin for your application. And finally, MathWorks has the key building block for developing digital twin for your IoT applications. Thank you very much.
Great, thank you, Terry. That was excellent. I'm curious, as you deploy these twins, that you showed some real examples, do they degrade over time and you need to go in and tune them, or do they self-tune? How do you guys think about that?
Yeah, that is the excellent point. So the digital twin, it is, evolve with time because it should, at any given time, represent the actual system. So some customer actually use the digital twin to do monitoring to make sure that when the degradation does happen, they can take action before that. So by constantly injecting the data into your digital twin model and make sure that it really represents the actual state of your machine is the key.
Great. Thank you very much.
Thank you.
I think now, let's see, we have just a few minutes for a couple of questions. So let me open it up to our panel. First question is from Katerina. Can you describe a case where machine learning was enhanced by simulation of a real-world system in order to understand the real world more clearly? I think we saw a couple examples from you. Terry, any other examples that the panel would like to highlight?
Yeah, recently we'd done a pilot, and in that, the system that we're trying to simulate was a wind turbine, and we were actually trying to look at fatigue-based failure on the wind turbine, right? The wind turbine was sensorized, but it's actually rotating machinery, right? So there's a limit to how much sensorized information that you could get from the wind turbine. So the pilot essentially involved taking, much in the same way that Terry showed it, involved taking actual sensor data from the wind turbine, supplementing or complementing that with virtual information that came from a virtual simulation model, bring the two together, right? Using the actual measured data to do things like calibrating the simulation model such that it provides the right response. And also, kind of merging the two data streams, the one coming from the actual sensorized data source and the one coming from the virtual model, bring them together to truly study what the stresses on the wind turbine were, what the path to failure is, and what the timelines to fatigue-based failure scenario are.
Great. Thank you. So we have one other question. There we go. So how do we balance consumer privacy and the industry's inclination to collect as much data as possible? That's a good question. Anybody want to take a... It gets encrypted in a quantum computer and everything's fine.
Can you repeat the question?
Yeah, how do we balance consumer... Can you put the question back up, please? Consumer privacy, I think, was the question. So we collect more data, we get more accuracy. So how do we balance consumer privacy and the industry's inclination to collect as much data as possible? I think this was taken right from the Senate testimony of the Facebook and Twitter execs this morning. Thank you. This is a wrong Twitter feed.
Yeah.
When it comes to engineering simulation data, at least, that's the business that kind of I belong to. There are no set standards. So there's obviously, we focus a lot on data privacy, right?
Yeah.
So any customer data that we have, we make sure it's secure and protected. But when it comes to using simulation data in an IoT context, right? So how do you take models? How do you take asset information, bring them together and study things, and related to that, how do you manage the privacy?
Yeah.
So I think there's this need for industry-based standards that we can then kind of conform to as suppliers, which I think are evolving right now. But yeah, that's maybe one way of doing it, by establishing standards for how we can consume, manage data.
Yeah, I'll take a little stab at this too, just because we have some experience with customers who have challenges with the sensitivity of this data. And for us at Hitachi, we help them with this multi-cloud kind of infrastructure challenge. So it really comes down to what data you house in a public cloud, what you might house in your own data center, what you store on the machine, and how you manage that data in a regulatory compliant way. So it gets kind of complex depending on the industry, but I know what we've found is it's the combination of the technologies that you've been discussing around digital twin, but the data itself then gets stored in a more sophisticated data infrastructure that can help manage the access to that data in a more granular way. So do we have time for any more questions? No more questions. You should have cut it off before that last question. Now, I'd like to thank our panelists. Hopefully you got a good survey of the emerging technology areas around digital twin, from the quantum computing, the physics-based simulations, the way that twins are used in practice. So I'd really like to give a round of applause to our panelists for a great set of presentations today. Thank you. And with that, I'd like to bring Bev back up on stage to introduce our next section.
Well, that was great. I don't know about you, but Scott sure scared me with the fact that quantum computing can break all our crypto systems.